Okay, so we're diving into some research you've sent over on time complexity analysis. And it seems like you're really trying to get a handle on why this matters,
hmm
especially in building like real-world applications. You ever that moment where your code runs perfectly in testing, like you're feeling invincible,
Yeah.
and then bam, real user data hits, and it's like everything grinds to a halt.
It's a tale as old as time itself, isn't it? That disconnect between small-scale testing and massive real-world data often comes down to time complexity.
Right, because it works on my machine, just doesn't cut it in production. So can you break down what time complexity actually means in a way that clicks for someone who might not be, a computer science whiz?
Absolutely. Imagine you're sorting something. Okay, sorting a deck of cards, no problem. It's over quickly. But sorting every book in a giant library, that's going to take significantly longer, even though it's fundamentally the same task. Time complexity is about understanding how the time required for a task grows as the size of the input grows.
So it's not just about the time it takes at one specific size. It's about how that time scales.
Precisely. And this is where things can get a little tricky with unit tests. They're essential for catching bugs, but they often use small data sets. Our source article had a great example, actually, of a social media app. In testing, with just a handful of posts, the feed loaded instantly, but when they introduced a power user with thousands upon thousands of posts, suddenly the feed became unusable because the code wasn't designed to handle that volume efficiently.
Oh, that's a developer's nightmare. You build something that sings in testing, and then real-world usage throws you this crazy curveball. It really highlights just how critical understanding this stuff is, especially if you want to avoid those user experience disasters. So it's like we need a way to classify these levels of efficiency. And the source mentioned Big O notation. Now, before I run for the hills, is this where it gets really math heavy? Like what even is Big O notation?
It's not as scary as it sounds, I promise. Think of Big O notation as a way to categorize how an algorithm's runtime grows as the data it handles increases.
Okay, so a classification system for efficiency. The source mentioned a bunch of these big O things. Where do we even begin?
Well, let's start with the gold standard O1, which means constant time.
Constant time. Sounds amazing.
This is the holy grail, because no matter how massive your data set gets, the operation takes the same amount of time. Imagine picking a card from a shuffled deck, whether it's a single deck or 1,000. The time to find your card, ideally, remains the same.
Okay, so if O1 is the holy grail, what's next in line,
Yeah.
on this efficiency ladder?
Next up is O log n, logarithmic time. It might sound intimidating, but it's actually a sign of a really clever algorithm. Think of it like searching for a word in a dictionary. You don't flip through every single page, right?
Wait,
You start maybe by opening it somewhere in the middle, see if your word is before or after that point, and then you cut the search space in half. Then repeat.
like that game where you guess a number between 1 and 100, and you keep having the possibility. I never connected that to algorithms.
Precisely. Each step reduces the problem size exponentially, making it super efficient for large data sets. Now, our source also mentioned O(n) log n, which is often seen in sorting algorithms like merge sort. Even though it seems more complex, it's significantly better than something like O(n)2, which represents quadratic time.
Okay, so the bigger that exponent gets, the scarier the runtime. Tell me more about this ON2. It sounds like it could spiral out of control pretty quickly.
You're catching on. O(n)2 essentially means that for every element in your data, you might have to do something with every other element. It's manageable with small data sets. But as your data grows,
Yikes. Recipe for disaster.
it can bring things to a crawl. Imagine having to compare every single book in a library to every other book. Not very efficient.
And I'm guessing O2N is like the abandoned ship signal of time complexity.
You could say that O(n) is exponential time, and this is where things can quickly become unsustainable. For each additional element you add, the runtime effectively doubles.
Whoa.
It's a clear sign that a different approach is needed, especially if you're dealing with, well, anything beyond the tiniest data sets.
So we've gone from lightning fast constant time to potentially melt your computer exponential time. It's amazing how much the choice of algorithm can impact performance,
Yeah.
even if the task seems, kind of similar on the surface. All right, so we've gone from Big O sounds scary to actually understanding these different levels of efficiency. But how do we actually, put this knowledge into action? What can we do to write code that doesn't buckle under the weight of real-world data?
That's the million-dollar question, isn't it? And the good news is there are some practical strategies we can use.
I'm all ears. Hit me with that time complexity busting wisdom.
First and foremost, choosing the right data structures can make all the difference. Think of it like this. You wouldn't use a hammer to tighten a screw, right?
Yeah.
If you need lightning-fast lookups, a hash table could be your best friend.
Okay, hold on. Can you break down hash tables for me?
Okay.
What makes them so fast for lookups?
Absolutely. Imagine you have a giant library, right? But instead of searching shelf by shelf, you have this magical system that tells you exactly where a book is located. That's essentially what a hash table does.
Okay.
It uses a function to assign a unique address to each piece of data, allowing for near instant retrieval. We're talking about that desirable O1 average case performance.
That's a really elegant solution. So by simply switching to a hash table, you can drastically improve the performance of something like, say, that social media feed from earlier.
Precisely. Instead of searching through a massive list of posts every time, the app can use the hash table to instantly grab the relevant posts. It's all about selecting the right tool for the job. Now, another common culprit for poor time complexity is the dreaded nested loop.
Ah, yes. Nested loops, often a necessary evil in programming, I feel like.
Yeah.
But what makes them so detrimental to performance?
Well, they often lead to that ON2 quadratic time, which, as we discussed, can be a major performance bottleneck as your data scales. Imagine having to compare every single book in a library to every other book.
Right.
Not very efficient.
Definitely not.
Sometimes refactoring your code to achieve the same outcome with a single loop or a more efficient algorithm can work wonders.
It's all about working smarter, not harder.
Yeah.
Right. The source also mentioned something about code reviews being really helpful in this process.
Absolutely. Code reviews are invaluable, even if the reviewer isn't a time complexity guru. Having a fresh pair of eyes look at your code can often help identify potential bottlenecks or areas where a different approach might be more efficient.
It's like having a second brain to bounce ideas off of.
Yeah.
So we've gone from zero to understanding why this stuff matters. A&D having some tools to write more efficient code,
Yeah.
all without like completely overwhelming ourselves.
Exactly. And remember, this is just the tip of the iceberg. Your research mentioned that time complexity doesn't just impact speed, but also resource usage.
Oh, right.
Think about a mobile app with a really resource-intensive algorithm.
Yeah.
It could drain a user's battery life faster than you can say big O.
That's a thought-provoking point to end on. It's not just about making code faster. It's about making it smarter and more responsible in how it uses resources.
Mm-hmm.
Well, there you have it, a crash course in time complexity analysis. Until next time, keep those algorithms efficient and those brains engaged.